All right, guys. Now, guys, I am slowly replacing last year's videos with current videos. Obviously, when you guys were on the big blue button, I didn't screen capture and I kept last year's videos, and now I'm slowly replacing them. So, oh gosh. I'm obviously not ready to start screen capturing, but let's get to this page. So we can split our radiotherapy into two. Diagnosis, we want to try and detect abnormal cells. And as was said yesterday, we can do that with either a radioisotope tracer, which you can attach to a molecule, and then that molecule can go to the desired organ or location, or you can do it with a PET scan. Same deal. The tracer will emit a gamma ray. The PET scan will be emitting positrons because it's a beta positive, and then that annihilates into a gamma ray. The one thing with PET scans, when you annihilate your mass, you could take the mass of an electron in atomic mass units and times it by 931, you will get 0.511 MeV. All right, so you just have to change the frequency of your camera and it will be able to detect the same kinds of images. The next one is therapeutic uses. So now we've found the tumor. We've localized it. We might have taken a little biopsy of it and gone, yep, this is a bad tumor. It's growing rapidly, and if we leave it, it's going to keep taking over and it's going to cause bad stuff to happen. So now we need to treat it. And as I said, your doctor, your surgeon, your radiologist will be discussing that, you might be able to chop the damn thing out. It might be enclosed in a capsule and you can remove the whole thing. Or maybe it's attached itself to a major artery and you can't, because if you try, you might cut that artery, things like that. Maybe it's so far in the middle of an organ that it's not possible to dig in there and rip it out. So maybe we want to attack it with radioactive particles, okay? So there is a number of techniques. Now, obviously, there's a ratio. You want to be damaging the abnormal cells while leaving the normal tissue unharmed. Okay, so there is a risk-reward ratio. Too much radiation might end up making the person sick, and then they become ill and die from the radiation instead of the tumor. Okay, so they need to weigh it up. One of the best ways to attack cancerous tissue is the gamma knife, and literally, it's a beam of gamma. It's a gamma ray beam, which we know is highly penetrating. So if your tumor is in the middle of your brain, you can focus a beam of gamma rays and it will travel through your brain and through that tumor, okay? Now, obviously, imagine a line going from the start of your head to the end of your head. All of that tissue is going to be irradiated. So what they do is they have you lying down with your head in a brace, and the beam will literally rotate around you on like a three-axis, not gimbal, but a three-axis mount. So you're just lying there for your half-an-hour session. You can't see the beam, you can't feel it, but it's going around. Now, if the beam is always pointing at that tumor, if the tumor is at the focal point, then as the beam rotates around, then your healthy tissue is not going to get as much of a dosage, okay? So that's why they need to identify where the tumor is and the size of the tumor, and then they might make a special brace for you to keep your head nice and straight. So there's the gamma knife. The next one, brachytherapy. This builds on Pierre Curie's, when he placed that piece of radium on his skin, it was emitting beta particles and it made a big grey calloused lump, and he went, maybe we could use that for treating cancer or tumours. What you do, you put a sealed radiation source inside or next to the tumour. So you just insert a metal pellet into the tumour and you leave it there, okay? So now that would need to be a beta emitter with a high activity and preferably a long half-life. You don't want that because it's quite invasive. This person needs to be sedated. The local area needs to be anaesthetized, and they stab you with this catheter and they inject little metal pellets. And they have to stay there for a couple of weeks, couple of months, and let the pellets do their damage. Okay? Now, this is commonly used in breast cancer, in prostate cancer, in some brain tumours as well. This is a X-ray of a person's pelvis, and you can see all of the metal pellets. All right. Now you've got to be careful. Don't just Google image search brachytherapy, because one of the most common treatments is prostate, and you don't want to see an image of somebody's meat and two veg while you're trying to find a picture of this. So this is an X-ray of somebody's a male's prostate. When they get old, the prostate organ is prone to getting tumours, and so you leave them in. And then let it do its, the doctors will say, all right, we'll leave it there for a month. The tumour will get a certain dose equivalent, and then we'll come and we'll remove those pellets, and then we'll have further diagnostic scans to see if the tumour is shrunk or died. Okay? As I said, your radiopharmaceutical, so rather than your radiopharmaceutical being a tracer to find the tumour, that we want it to emit gamma rays so that we can detect it with a camera. Now let's make that tracer a beta emitter so that when it gets to that organ, it can actually bash the crap out of it and try and kill it, rather than say, I'm here guys, if you want to find me with a camera. So rather than diagnosing, you can treat it therapeutically. Okay? So those are the three main ones. Your gamma knife, your brachytherapy, and your radiopharmaceutical. Okay? And then tagging antibodies, that's more of a biology medicine. Then there's just quick little applications in industry. So I'll get you guys to read this in your own time, because today I want us to look at rates of reactions and things like that. But you can use it to irradiate food, sterilize things. Oh, a quick little story. I tell this story every year. One of my mates, I met him in year 8, start of high school, and I'm still friends with him today. He went to my wedding. He had a girlfriend back when we were in our early 20s, and she was a bit crazy, but he dodged that bullet. He went to the Philippines, and he decided to buy his crazy girlfriend a present. So he got this wonderful little wooden drum, and it had some skin that had been stretched over the drum, and it had these little ornate ropes that tied the skin to the drum, and it had these little beads, and boom, 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 boom. It cost him $30, $40. He's like, this is a great present for my girlfriend. He brings it back to Perth, comes through customs, and he declares it as an item. Custom looks at it and says, no way, that's not coming into Australia. That's got wood, it's got skin materials, it's got nuts and seeds on it. Sorry, you're not bringing that in to the country. You've got two options. For free, we will destroy it. We will destroy it and get rid of it for you, put it in a furnace, see you later. Or for $190, we can blast it with gamma radiation. You can come back in 2 weeks' time and you can collect it. And my stupid friend went, I really like this girl. I'm going to pay for the gamma treatment. So he paid the extra 150 odd bucks. And they put it into a machine. They would have blasted the heck out of it with gamma beams. Any biological material, any parasites, any seeds, nuts, weevils, maggots, ticks, eggs, whatever you name it, would have been just killed. Okay, so basically just blasted all the DNA, and then now it's safe to come into Australia with our wonderful, unique flora and fauna. Okay, so just have a read of that. And then, there's some wonderful questions which you could have done, and I encourage you to do. You have a lot of work to do tonight. Let's get on to rates and activity. You've seen this in the previous booklet. You've been asking Mr. Murray, when are we getting to the rates and activity? This is the fun stuff. Let's get going. All right, so we're going to use dimensional analysis. Remember, it is our friend. There's no real equation for rates and activity. You can create an equation, but it's better to look at your activity is going to have the units of events per second, all right? So N just stands for an event, okay? So like a becquerel. If it's 100 becquerels, then it's going to be 100 events per second. So it's 100 N per S. Now, if we multiplied that by energy per event, now there's a couple of ways we could do it. We could have joules per second, or we could have MeV per second. Remember, we've got 2 units of energy, and you need to be able to convert between the two. Then if we then multiplied it by time, which is always in seconds, wait a second, energy per event, that's not the right dimensional analysis. Try again. What should it be? It should be joules per N. Sorry about that. Let's see what we get. Let's use dimensional analysis. Ns to the negative 1. Jn to the negative 1 times S. And we get some cancely. We get the seconds cancel with the per seconds, and the N cancels with the per N. And we're left with a unit of joules. Okay? One thing, though, is our activity, we have to assume constant. And what that means is that your time has to be much less. Have you ever used that many less thans in maths? I don't know, I'm making stuff up. Your time interval has to be much less than your half-life. Okay? So if the half-life's 6 hours and your time goes for 12, well, you're assuming a flat line, but we're actually asymptoting. But if your half-life is like a year, or in your smoke detector, the half-life is like 90 years, and we're looking at the activity over a week compared to 90 years is not significant. The activity is not going to drop. So when you buy a brand new radioisotope smoke detector, it's typically 37 kilobecquerels. And after 90 years, it will have dropped to half of that. So in the lifespan of your smoke detector, the activity hasn't really dropped.
So why do you need radiation in your smoke detector?
Well, yeah. When I started teaching, radioisotope smoke detectors were all the rage. It's what every year 11 kid wanted for his birthday.
I know.
Nowadays, there are newer models that use infrared to actually detect the heat coming from things rather than the smoke. So the newer ones are more, they're detecting light rather than smoke particles entering the chamber.
So they're
Let's just
detectors rather than smoke detectors.
Ion detectors.
Fire.
Fire detectors. I've just realised I've gone backwards because I've just used the equation up here that we really want to put down. Let's just rewrite it for prosperity. Let's put it down here. We'll go activity, which is ns to the negative 1, times energy per event. Oh, now let's go MEV, n to the negative 1. Let's suppose that every alpha emission releases 5 MeV. I'm not telling you what it is in joules. Which shouldn't matter because when it comes out and we do the dimensional analysis, we're left with a unit of energy, but it just happens to be in MeV. So, who remembers how to convert? Oh, go, yes.
EV
Yep.
is 10 to the negative 19, 1.60 times 10 to the negative 19.
Is the 1.66?
Nope.
No, that's kilograms.
That's the mass unit into kilograms.
1.60
So 1 MeV, you would...
times 10 to the negative.
Good. All right. So, just remember that. If we ever need to convert between MeV and joules, you need to know those conversions. All right. In your data sheet is this one. All right. But also in your data sheet are your metric prefixes that mega equals 10 to the 6. Okay. I'm happy for you to just jump into that one. All right. So if you just go multiply it by 1.6, 10 to the negative 13, you can convert it to joules. Oh, look. Here's my americium smoke detector. Perfect. My activity. Remember? 10 to the 3. We've got energy per event, and we've got event per second. Okay? So the power of the smoke detector, I've skipped one. That's just going to be, instead of multiplying by time, let's just go back. I'm too excited. Let's just go back one step. Energy per event. if I look at dimensional analysis there, we see that the per events cancel with the events, and we're left with joules per second. All right, so if we times the activity by the energy per event, then we're left with the rate of energy with respect to time. Okay? So that's what the first question. Hello, who are we chasing?
Sorry, I'm looking for Sam Rose.
Sam Rose.
He's not here today.
Ooh, he would normally be sitting there. Not here.
Okay.
I haven't done attendance, sorry.
Okay, no worries.
He's not here.
So he's not here? No.
Possibly away.
Okay.
I haven't checked the attendance yet. Sorry.
Thanks, no worries.
So, is that a new maths teacher?
No, it's oral stuff.
Oh, new.
Yeah,
Oh,
French, test.
Tuesday. You've got assessments on. He's dodging the assessment. Dogging the French boys. So, do we have an equation? Well, not really. What do we do? Energy per event times events per. You're not really getting events per time. There's no real equation. So we're just going to multiply. Whoop. Where are we? 5.486 times 10 to the 6 over n multiplied by n over... Oh, hang on. N is 37 times 10 to the... We're just going to multiply them, right?
Can we just do power energy?
So you're just going to multiply them. There's no real equation. I'm getting a little bit caught up here. We end up with 2.03
So activity equals N on T.
times 10... I see what I've done.
Yeah, it's over.
No. Let's just do that. So we're going to go MeV per second times by 337
It's not.
per event over n per second. We will be left with, cancel and cancel, we'll be left with a unit of MeV per second. So we'll end up with 2.03 times 10 to the 5 MeV per second. And this is where Vidler comes in and very confidently goes, let's now convert that unit of MeV, and then we will get joules per second. Okay? Now remember, it's not very large. On an atomic scale, that's a huge amount. But for us, when your calculator spits out 3.25 times 10 to the negative 8 joules per second, that's nothing. That's 32.5 nanowatts. I mean, we don't ever really use the metric prefix of nano.
So you pulled an engineer. You've done it.
I know, I've gone the engineer. I was going to go 0.032 microwatts. That would also be engineering notation. So now we've got that power. Let's just keep that power and then come down here and just go energy is power times time. We've got that in our data sheet.
No, in the events per second, the first equation, it's 37 times 10 to the 3 instead of 3.7 times 10 to the 4.
Ah, okay.
So what do we assume the units of power are?
Watts, which is a joule per second. So it's not MeV per second. We're always going to go joules per second is the watt.
Yeah, but the question
Can
asks
we write joules per second?
You can leave it as joules per second or you can leave it as watts. Those units are both fine.
would it be better to write it as joules per second? Because it's
I've done both. I've done MeV per second. Hold on. I've done that. And then I needed to convert to that. Okay? So there was no real need to use the unit watt. Yep.
First equation, P equals En times E on N.
Yep.
times N on T.
Yep.
So the E on N.
That's energy per event
Yeah.
multiplied by activity.
So activity equals N on T.
Yeah. And again, there's no real equation. If
How
you
many number of events have there been? We don't know.
37,000 every second. So 37,000 every second, and every one of those provides 5.4. So you multiply them together, you're going to get the total energy in a second. Okay? So if we go down here, remember time needs to be in a day. Yes, it needs to be in a day. It needs to be in seconds. So when we're down to here, we've got joules per second. Let's just go 3.25 times 10 to the negative 8 joules per second multiplied by, we can't just do 1 day because then the units don't mesh up. So we now need to get it into seconds. So 1 times 24 times 60 times 60. And that will give us seconds. So you don't need to do this step, but I'd like to inform you that there are 86,400 seconds in every day. Okay?
Rise that haven't.
Yeah. And so again, dimensional analysis shows that the seconds cancels with the per second, and we get 2.83 times 10 to the negative 3 joules. Okay. Now let's just go with it. This is joules per day. I'm just being a bit cheeky now. I'm going off script. We've got for every day that amount. So we could continue on with dimensional analysis. We could go 2.83 times 10 to the negative 3 joules per day. I would then need to multiply by a unit of days. So if I had day here, then my day multiplied by my per day would give us joules. But currently I've got years. I've got to convert that to days. So let's go 20 times 365.25 days.
7,305.
Cancel.
What if we forget to write 0.25?
You'll be off by something that should not be significant. Just check that because I get 20.5.
20 times 365.
Times by the energy per day.
Oh, yeah.
And you get 20.5. Okay? All right.
Yeah, 20.4.
1.28 times 10 to the 20 electron volts.
I don't think.
Yeah. You could go backwards, but we'll leave it in joules for
I
now.
don't think you did it with 0.25.
Let's keep going because we're running out of time. We have a power here. That's 1 times 10 to the 6 joules per second. All right? Here we have energy per event. But this is MeV per N. Now here's a problem. We've got joules and we've got MeV. At some point we're going to have to convert one or the other.
Yeah.
Okay? So what have we got? We had power equals activity multiplied by our energy per event. And we're being asked for the activity. What is the number of events per second? So this value, oh geez, that's not a highlighter. Let me just change this to a highlight. No, where are my highlighters? There we are. So we want to find that, okay? So again, I've tried to make an equation here so we can then rearrange. Well, we could say, well, activity is going to be power divided by energy per event. Okay? Hold on. We need to do our conversions. So let's convert our joule. It doesn't matter which one you do. Okay? You can convert joules to MeV or MeVs to joules. You will see that they cancel if they're the same. All right? So maybe I'll draw a big fat line down the middle. Let's do both. All right? So let's convert our 1 megawatt equals 1 times 10 to the 6 divided by 1.60 times 10 to the negative 13. And this will give us MeV per second. Okay? So I've gone from joules to MeV. I don't think I've done it this way in the previous... No. So let me just do this now. 1 times 10 to the power of 6 divided by a really small number is going to give a really big number. And that should make sense because an MeV is a tiny unit of energy. 6.25, 10 to the 18. Yes, That many MeV per second. It's a lot. So now, let's just check our equation. We'll go activity equals power 6.25 times 10 to the 18 MeV per second divided by energy per event, which is 200 MeV per N. All right, I'm going to run out of room here, but look at my dimensional analysis now. We're going to get the energies cancel. The s to the negative 1 stays there, but now we've got a 1 over n to the negative 1, which should just give us n. So if I look at the dimensional analysis, I'm going to get n s to the negative 1. I'm going to get events per second if I do it this way. So if I take that number and divide it by 200, I get 3.13 times 10 to the 16.
So how did you, where did the activity come from
N over 2.
in the first?
Hang on, ask me that question in 3, 2, what was your question?
Where did activity come from in the first equation?
Well, that's just an equation that we attempted to derive in the previous page. You said power, if we go back up here, power is activity multiplied by energy per event. Okay? Now, the problem we had with this question is we had joules and MeV, so one needed to be converted. So, with my red pen now, let's convert this one to joules per event. Okay? So, over here, I'm going to write energy per event equals 200 times 1.60 times 10 to the negative 13. So that will convert my MeV into joules. So we'll now get joules per event. 200,
It's 3.2 times 10 to the power minus 11.
joules per event. So each fission event releases that many joules. Now let's use the same equation. A equals, and I'm going to use dimensional analysis here. I'm going to use my joules energy power. Where's my power? My power is 1 megawatt. It's 1 megawatt, which is 1 times 10 to the 6 joules per second. Hang on, let me color code this. And then we're going to divide that by energy per event, which we just solved as 3.2. And so you can see now, we did a conversion. The joules will cancel. We've got s to the negative 1 divided by n to the negative 1. So we get a double inverse. You'll end up with n s to the negative 1. I am so confident that it's just going to be that number there. I'm not even going to go to my calculator because it's going to be 3.13 times 10 to the 16 n s to the negative 1. Okay. Just before we go on, do we have any room at the back of the booklet? Back page? Just go to the back page because I want you guys to work on questions 4 and 5 on your own. But another interesting question that can be asked, can I leave it like that? I might not. Let's just say if the mass of uranium-235 is 235.043923 atomic mass units. And that I took from the table of masses. Then how many kilograms of uranium do I have per event? Okay. So I want to get this into kilograms. So in our data sheet, we can times it by the number that I think Matthew mentioned before, 1.66 10 to the negative 27. That will get my atomic mass units into kilograms. So the mass of one uranium atom is 3.90 times 10 to the negative 25 kilograms per event. Now I'm ignoring the neutron because my fissile nucleus is just sitting there and the energy's there and the neutron's going to come from a different event. So we're going to ignore that one first neutron that caused all this. Well, what could we do? We could multiply the kilograms per event by events per second. And what would we end up with?
Kilograms per second.
Excellent. We would get the kilograms of uranium. Now, if you multiply them, you'll get the kilograms of uranium every second that's undergoing fission. That's a kg. So let's multiply our kilogram per event. And the event per second is the value that we found. Every second there is 30,000 billion nuclei undergoing fission. You'd think, wow, that's a really big number, but it's not, because remember, we've got a lot of atoms to play with. So, there's more stars than there are in the universe.
I doubt that.
Google it. So we take the mass of one event, the mass of one atom, multiply by how many atoms are going in a second, we get how many kilograms per second. It's not much. We get 1.22 times 10 to the negative 8. Every second we lose that much mass. And again, dimensional analysis, cancel-y. We're left with the units. There are no equations. We're just taking our values. But in these questions, bring the units along. Because not only do the numbers do their dance, but the units do their dance as well. So in year 9 and 10, here's what we do. In year 9 and 10, we do this. And we go, all right, kids, get your calculators out, multiply the numbers, and your answer's going to be joules. But in year 11, I want you to go, well, hang on. The units are also being multiplied or divided or raised or inverted or added and subtracted. So, okay, how about in a year? So I want to have a number of years per second. So what if I said, just write in a year. Now normally what would you do? You would say, okay, I need to multiply that by how many seconds there are in a year. What would you do?
86400.
Times 356.25. 365.25.
You got 7 minutes, and also 3.31 times 10 to the 20.
What?
That's how many atoms there are in the average grain.
More stars there are in the universe. So in a year, what are we going to do? You would say equals, let's go the long way, 365.25 times 24 times 60 times 60 seconds per year. I'm going to write that in my dimensional analysis blue. Seconds per, no, that's just one. Seconds per year. That's a funny way to write it, but I'm just going to write it as S per year. So then, if I multiply that number, by that number, the seconds cancel. We're left with kilograms per year. So let me just write it all out all together. We'll go 1.22 times 10 to the 8 kilograms per second. Yep, thank you.
So should we write units in the test?
Multiply, hold on. Oh, I didn't work out what that number was, but okay, let's just write it all out. 365.25 times 24 times 60 times 60 seconds per year. All right, I've just abbreviated my year. Cancel-y cancely, and you get 1.06 times 10 to the negative 3 kilograms. Oh, no, it's not. Sorry, that was... Oh, could somebody do that sum? I did it per day. I need to multiply. 385 kilograms per year. So this is an actual type of question. That's how much fissile material you would need in a year for your reactor to operate continuously at 1 megawatt.
Assuming your activity.
But 1 megawatt.
100% efficiency as well. We haven't factored in efficiencies. If it was a 10 megawatt reactor, we'd need 3 kilos. But remember, here's the problem. You don't know what fissile, like in a bomb, they say about 1% of atoms undergo fission. The remaining 99% just needed to be there just in case. It's the same with a fuel rod. So you can't just say, you can't just dig into open up the shelf here and go, here's my 3 kilograms of uranium. That can power my 10 megawatt reactor for a year. No, only 1% undergoes fission. So unfortunately, you would need 100 of these. You would need 300 kilos, put them in your fuel rods. Only 1% is going to undergo fission. You can take out your spent fuel rod and then you can try and refine the fuel that didn't undergo fission. All right? But once your enrichment drops below a certain level, don't ask me what it is, once it goes below a certain level, it's now considered a spent fuel rod. Guys, as Minchin said, you guys have nowhere to be. I'm happy for you to hang around for an extra 10 minutes if you must. You must. Guys, have a look at questions.
So, can you then turn that into...
4 and 5. Have a go.
It was 1.3%, I think, in some ones.
1.3%.
Yeah.
So I was correct to 1 sig fig.
Yes.
Yes, Cameron.
could you then turn that into joules per kilogram here?
Oh, let's try it.
Well,
Joules per kilogram.
yeah, because it'd be power.
The joules cancelled when we multiplied or divided the power by the activity per event.
Okay, joule years per kilogram. Oh, no.
I don't know what you'd have to
No,
multiply.
just megawatts per year.
This here is how
Megawatt
many.
years per kilogram.
This is fuel per unit time. This is mass per unit time. The energy's got cancelled out. So you'd have to then multiply it back to joules per kilogram. And then, now if you multiply it by joules per kilogram, you would have joules per year. So you can play around with these values. If I said, all right, now let's go and multiply by how many joules per kilogram, there is...
No, it'd be watts per
It'd be a very
kilogram year.
big number. You would have lots of joules per year. So there's so many different ways. You can multiply these units by whatever you want, but you'd have to do the dimensional analysis to figure out what you ended up with. Okay? Now guys, just give me 2 minutes. I'm going